for the next week and a half or so is stoichiometry. Okay, this is chapter 12 in your textbook. Okay. Stoichiometry is a Greek word. Okay. And like all those things, if you know what the roots are, it makes it easy to understand. Stoich was the Greek word for element. The tree means to measure. So stoichiometry is the tree measuring elements. That's where they got the word from. And measuring is about how much. It's more than just elements. Okay? What it really is the calculations of quantities. How much? Based on a balanced equation. So our tool in figuring out how much is going to be the balanced equations. So we're going to have to look at those balanced equations. And look at how we interpret them. Okay, and the first way we want to interpret them is the way you did it in the bell work today. Okay? Okay, I wanted you to think about those balanced equations in terms of little tiny pieces, in terms of particles. So we want to be able to read those equations, because those equations are sentences. We want to be able to talk about it in terms of what it means in terms of particles, so we have to know what kinds of particles we have. So if you have an element, it's usually an atom. The smallest piece of an element is an atom. What makes iron is that every atom is the same. Every one has 26 protons. Okay? Second kind of piece you learned before we got here was molecule. There's two ways to get molecules. One is a compound. Okay. The ones where we use prefixes, the ones where they're both non-metals. Okay. And the other kind of molecule is for elements that are diatomic. Because the air we breathe is oxygen, but it's not atoms of oxygen, it's molecules of oxygen. We never breathe O, we breathe O2. We never breathe N, we breathe N2. Right? We breathe them in groups of two. And those are the ones they taught you about in 8th grade, and we had to introduce a new one for the compounds that weren't molecular. Remember what that third kind of piece was? One that's only based on the formula. It's the formula unit. An ionic compound, something made up of a metal and a non-metal. The reason we can't call it a molecule is we don't know which sodium gave its electron to which chloride. We just know that there's positive sodium attracted to negative chloride. And the charges cancel out, it's one apiece. So our formula makes our unit, 1AA, 1Cl. Okay? So this is our bell work. So how would we interpret this in molecules? Well, there's a 2. What did you draw? Well, you should have drawn something that looked like this. You know what your bell work answer should look like? You got 2 H2s and an O2. I made O bigger. Made 2 H2Os. Now, that's it in pictures. We got to say this, but remember, this is a sentence. So to say that as a sentence, I would say there are 2 molecules of hydrogen and 1 molecule of oxygen. Make 2 molecules of water. Now, this time it was all molecules because we had nothing but nonmetals and hydrogen. It's not always molecules. So let's do the same thing with an equation where it's not necessarily all molecules. So okay. So 2Al2O3 makes 4Al plus 3O2. Balanced because I got 4 ALs on both sides and 6 O's on both sides. So all to interpret this in terms of parts, all we have to do is decide what kind of part that is. So 2, what kind of part is Al2O3? Well, we only have 3 choices: atom, molecule, or formula. Aluminum's a metal. Oxygen's a nonmetal. I got 1 of each. That means this is ionic. If it's ionic, the kind of piece is a formula unit. So I knew that was a formula unit because aluminum was a metal, oxygen was a nonmetal. Form. That's my arrow. 4. What kind of piece is Al? Okay, we've got 3 choices: atom, molecule, and formula unit. Is aluminum by itself? Yeah. Is it diatomic? No. So that means the piece is, it's an atom. You would draw just 1 circle if you were to draw, right? It wouldn't be connected to anything. That's an atom by itself. And that's 4 atoms of Al. And the plus sign. 3. What kind of piece is O2? It's an element, but it's diatomic. So it's a molecule. So on tonight's homework, when it asks you to interpret in terms of particles, that's what you have to do. You have to decide what kind of particle it is. Is it an atom, a molecule, or a formula? Make sense? Let's do one more example of another equation. This is what happens when you throw sodium into water. Sodium reacts with the water, makes sodium hydroxide, which is lye, stuff used to clean out drains, and hydrogen, which is a flammable gas. Gotta be careful you don't light it on fire, it shoots the stuff across the room. So we're going to want to interpret this in terms of particles. All we're going to have to do is add what kind of particle it is. So I'll start off with a 2, because there's a 2 in front of an A, Na. What kind of particle is Na? Is it an atom, a molecule, a formula unit, or an ion? Well, one capital letter by itself. If you were to draw a picture, you draw just one circle. That's an atom of Na. And 2, what kind of piece is H2O? Atom, molecule, formula unit, or ion? It's got 2 elements, so it can't be an atom. It's a compound. What kind of compound? Is it molecular or ionic? Well, it's made up of just nonmetals and hydrogen, so it's a molecular compound. So it's a molecule. This shouldn't be new stuff. We've done it a couple times before. It goes back to same decisions for naming stuff. If you're going to put a prefix on it, it'd be a molecule. If you're worried about Roman numerals, it'd be a formula unit. Form, that's the arrow. 2, what kind of piece is NaOH? NaOH, well, it's not an element, because it's got 2 capital letters, 3 capital letters actually. So it's got 2 different kinds of compounds, ionic or molecular. Well, sodium is a metal, positive piece, right? So OH is negative, but we've got positive, negative. Those are ions. That's ionic. If it's got a metal in it, it's ionic. And if it's ionic, the piece is formula unit. So what kind of piece is going to fill in the blank this time? Okay, 1 capital letter, so it's an element. But it's not 1 atom, it's 2. So it's not an atom, it's a molecule again. So what this sentence is describing is the picture you would draw for this reaction. You'd say, okay, I got a couple of NAs. An O, an H, an O, an H. So over here I've got my 2 NAs, but now they're hooked to an O and an H, O and an H. You got an H2 left over. So these are atoms. These are more than atoms, and since it's oxygen and hydrogen, it's a molecule. This is more than atoms, and since it's a metal and it's got a metal in it, it's ionic, so it's a formula unit. This is 2 atoms stuck together, so it's a molecule. This is going to be non-metals stuck together when you make the diatomic. Make sense? So we can look at these reactions as if they happen 1 particle at a time. The reason why we balance this is for order this to work out, I got to make those whole pieces. If it's not balanced, I'm not making whole pieces, or I'm leaving off atoms. Okay? I don't want you to write this next piece down. I want you to think about it. So here's our equation. Hydrogen and oxygen make water. And then we said we said 2 molecules of hydrogen and 1 molecule of oxygen makes 2 molecules of water. So, is this sentence true? Would 2 dozen molecules of hydrogen and 1 dozen molecules of oxygen form 2 dozen molecules of water? Dozen means 12. Like a dozen eggs. Okay? If I did this 12 times, if I did it 12 times, I would use 2 times 12 pieces, right? That would be 2 dozen. I'd use a dozen pieces there, right? And I'd make 2 times a dozen pieces. If I just did it a dozen times. So I can just stick the word dozen in there after my coefficients, and it's going to be true. Let's try it with a bigger number. Could I do 2,000 molecules of hydrogen and 1,000 molecules of oxygen make 2,000 molecules of water? Just do it 1,000 times, right? How about a bigger number? About 2 billion molecules of water. Billion? 10 to the ninth. And 1 billion molecules of oxygen make 2 billion molecules of water. Is that going to work? Just do it 1 billion times, right? Let's try a really big number. What if I did it 6.02 times 10 to the 23rd times? Just a big number, right? It would still work. But I do not want to write 2 times 6.02 times 10 to the 23rd molecules of hydrogen. There's another way of writing that that's a lot shorter. I can replace all of this with one word. That's 2 moles of hydrogen and 1 mole of oxygen makes 2 moles of water. And that is the main new thing we're learning in this chapter, is that we can read these equations in moles. The reason why we can read them in moles is because we can read them in particles. And we just do it a bunch of times. Make sense? If I just do it a bunch of times, my particles turn into moles. So now we can start writing. So interpret this in terms of moles. Your homework is going to ask you to interpret equations in terms of particles. We saw that first. Then it's going to ask you to do it in terms of moles. This is how you do it in terms of moles. 2 moles Al2O3. Form. You got my arrow. 4. The next word is. Just put the word moles in. 4 moles of Al and 3 moles. Oh, this is the abbreviation for moles, the laziest abbreviation ever. Oh, it's easier, yeah, because all you have to do is stick in the word mole. But it works because we have atoms, molecules, and formula units, because we're counting the pieces. We're just counting them bunches at a time instead of individually. Make sense? So the coefficients tell us how many kinds of moles. Coefficients tell us moles. So I'm going to be able to start talking about moles of Al2O3 and end up talking about moles of O2. In the last part, your book talks about it as interpreting it in terms of mass, but what it really is we said the reason why equations are balanced is because atoms can't be created or destroyed, right? And we said that made true the law of conservation of mass. The coefficients tell us moles. Okay. So we said atoms were never destroyed, and that made sense, so that means the mass was going to be the same before and after. Have you noticed we never checked that? We never saw if the mass before and the mass after was the same. We just said it was going to be because we didn't know how to do it yet. Now we know how to do it. We have enough tools at our disposal. We can check because we can interpret the equation in moles. And moles, I can turn into grams. Make sense? So when they say interpret it in terms of mass, what they're asking you to do is make sure that the law of conservation of mass works. So we're going to check with this one. We drew pictures that said all the atoms were still there. We talked about those pieces. We said we could interpret it in terms of moles. So on my reactant side, if I'm going to interpret this in terms of moles, I have 2 moles of H2. Just copy that down. And I want to turn that into mass. So I need to get rid of moles of H2 and turn it into grams of H2. Hydrogen is 1.01 on the periodic table, so 2 hydrogens would be 2.02. So my hydrogen is going to weigh 4.04 grams. My other reactant was a mole of O2. I can go from moles of O2 to grams of O2. Look up O on the periodic table, it's 16. It's O2, so I double it. That's 32. And 1 times 32 is 32. Now, if I add those 2 numbers together, that tells me that my reactants weigh 36.04 grams. Because 4.04 plus 32 equals 36.04 grams. Okay, remember that number, we'll need it again in a second. Okay? That's how heavy my reactants are. If I'm going to prove the law of conservation of mass is true, I've got to figure out how heavy my products are. So how much H2O? Well, there's a 2 in front of it, so I have 2 moles of H2O. I'm going to get rid of moles of H2O and turn it into grams of H2O. That's 2 H's times 1.01 grams, 1 O times 16.00 grams. That's 2.02 grams, and 16.00 grams is 18.02 grams. Add up the numbers on the periodic table. That's why we learned how to do this. Okay. And that adds up to 36.04 grams. But just a second ago, we said my reactants weighed 36.04 grams. And I just figured out that my products weigh 36.04 grams. It's going to work every time. Okay? It's going to work. If it doesn't work, you did something wrong. Reactants and their products are going to be equally heavy. If you got either you don't have a balanced equation, you looked up a wrong number, you added badly, it's going to work every time. So what I did was added up how much each chemical weighed on the reactant side and on the product side, and then added up the reactant side and the product side, they're going to equal each other. Make sense? Okay. So let's try it with the other reaction we've worked with. 2Al, 2O3 makes 4Al plus 3O2. Does that work? Well, the answer is yes, but how do we prove that it follows the law of conservation of mass? Start off by saying I have 2 moles of Al2O3, and over here I've got 4 moles of Al and 3 moles of O2. get rid of moles of Al2O3, change it into moles, oh, sorry, change it into grams. And 2 aluminums times 26.98 grams is 53.96 grams of Al. 3 O's times 16.00 grams is 48.00 grams of O. So altogether that weighs 101.96 grams. And 2 times that is 203.92 grams. Okay. Now I just got to work on the products. Moles of Al, change to grams of Al, and that's 26.98. So 4 times 26.98 is 107.86 grams of Al. 3 moles of O2, 1 mole of O2 is 32.00 grams. So that adds up to 96.00 grams. That didn't work out. What did I do wrong here? No, it's got to be a 2 here. That's what's wrong. 26.98 times 4. Try to do it in my head. 27 times 4 is 108 minus sine 2. So if I add those up, 107.92 grams plus 96.00 grams, I get 203.92 grams, which is the same as my reactance work. And it's going to work every time. So when they say do it in terms of, they say in terms of particles, got to decide what kind of particle it is. They say in terms of moles, just write the word moles after coefficient. And if they say mass, what they're asking you to do is prove that it follows the law of conservation. Each reactant add up, each product add up. The 2 should add up together, add up to equal each other. Because mass is going to be conserved, or you did something wrong. Really tough? Why we're doing all this. And we're not going to do this math today, but what we're going to do is now we're going to be able to we're going to go from moles to moles. In the past, we turned moles into grams, right? Or liters or particles. Now we can turn it into moles. So this equation says every time I use 2 moles of Al2O3, I make 3 moles of O2. Doesn't that equation say that? I also make 4 moles of Al, but if I'm going to use 2 moles of Al2O3, I'm going to make 3 moles of O2 every time. Hey, those 2 are equal to each other. And if they're equal to each other, equivalent to each other, I can write them in conversion factors. Because if I use 2 moles of Al2O3, I'll make 3 moles of O2. Or I can put it the other way. Doesn't matter which one I put on top. Actually, I can make 6 different conversion factors out of this. Because I could also go between Al2O3 and Al. right? I could say for every 2 moles of Al2O3, I make 4 moles of Al. And I can flip that over. Right? So I can make 2 there. Or I could compare the Al and the O2. Because every time I make 4 moles of Al, I also make 3 moles of O2. So I can make conversion factors out of any chemicals in the equation. Doesn't matter which side they're on. It's just one I'm going to use, the other one I'm going to make. But I can make mole-mole conversions no matter which one, no matter where it's at in the equation. Doesn't matter if it's a reactant or a product. All that matters is that you got the right coefficients in front. And that's all I did was copy the coefficients from here. I copied the 3 in front of O2, in front of O2. Okay? And notice what these conversions are going to let me do. With this one, I'm going to be able to get rid of moles of O2 and turn into moles of Al2O3. So for the past month, everybody's asked me, do I have to write the chemical after mole? And I said, yeah, because eventually that's the part we're going to change, is the chemical part. This is where we're changing the chemical part. Okay? So just make sure. Which one of those can be made from this equation? Okay. Everybody got it? Figured it out? So did everybody see the right answer? Okay. So what's wrong? Why can't I just put moles of Al or moles of Al2O3? Because there's an implied 1 and 1, and there is not 1 mole of Al in 1 mole of Al2O3. So that'd be 4, and there's not just 1 mole of Al2O3, there'd have to be a 2 there. Copy the numbers from in front of copy the coefficients. So where it says Al and O2, the number in front of Al is not a 2, it's a 4. In front of O2, it's a 3. Sense? We can write them all. We don't write them all. But the fact that we can means we get to choose which one to write. And we ask ourselves some very familiar questions. What unit do you want to get rid of? Where's it got to go? What can you change it into? So we said we were going to be able to learn how much. We have learned the secret to this unit already. It's that mole-to-mole conversion. I had to get to a point where you understand why mole-to-mole worked. It worked because it works in pieces. We just do those pieces a bunch of times. So how many moles of O2 are produced when 3.34 moles of Al2O3 decompose? So notice that we're asking about how much. How much is made? The calculation of quantities in a chemical equation using the balanced equation, stoichiometry. So this unit is all going to be variations on this theme. What we're going to do is add the grams to this, and the liters, and the particles. So where do I start this problem? Start where I start them all? By writing down what they gave me. It's 3.34 moles of Al2O3. I need both. I need to keep the moles. I need to keep the Al2O3. I need a conversion factor. What's got to go on the bottom? What do I want to get rid of? Moles of Al2O3, right? That's got to go on the bottom. What can I turn it into? Well, moles of what they asked for. They asked for moles of O2. And I copy the numbers from the equation. The number in front of O2 was a 3. The number in front of Al2O3 was a 2. I'm just copying those coefficients. Balance the equation so we can get the coefficients so we can do the math. So we can figure out how much we're going to make. I like it chemistry because it all fits together. It's not... Okay, so 3.34. The 3's on top, so you push times 3. The 2's on the bottom, so you push divided by 2. 3.34 times 3 divided by 2 equals 5.01. Okay. You're not going to have to do this. This is what we're going to do in class tomorrow, in addition to adding grams to this. Okay? Because let's go back to our idea. Last chapter, we had the mole in the middle, right? And we did grams, liters, particles. But now we got something else. We got moles of something else. Right? So all we've added to our diagram. Does that make sense? We found something else, moles were equal to each other. It's not one mole this time. So this is the only place that you don't put one next to moles every time. Up to this point, every time you put a number in front of moles, it's been 1. Now, you put a number besides 1 if you're getting them out of the balanced equation. Going from moles to moles, you put numbers besides 1. But if my next conversion factor, if I want to turn this into grams, I'd go from moles of O2 to grams of O2. And it would be 1 mole of O2 weighs 32 grams. I only use the coefficients when I'm changing from one chemical to another. Because that's where you got the coefficients from, where one chemical is changing into another. Make sense? So on tonight's homework. They ask you to balance it, to interpret it in terms of particles. You're going to write in atom molecular formula unit. Moles, you're going to write in the word moles and add up the balanced equations. Okay? Welcome back. Have a pleasant day.